All right, it is Advent of Code, day 24. Second to last day. Exciting. And here we go. Okay. Coordinates at other coordinates. Position and velocity. Ignore the z-axis for now. How many of their paths will intersect? Test for intersection between the paths they trace. Okay, that's pretty annoying. Because they don't need to be integer intersections. Check all pairs of hailstones future paths or intersections. How many of them occur within the test area? But they're only future paths. So note that they could intersect inside the area, but not actually intersect because they're going in opposite directions. Okay, so what I want to do is line intersection. First I'll parse the input. Or is it velocity or position and velocity? Px, okay, yep. How many are there? Oops. 300. Okay. Let's see. P1, B1. Actually. And now what we need to do is figure out compute intersection of these two things. I'm just gonna look this up. I don't know off the top of my head. Okay, do I believe it's this first one? Maybe. Okay, so that's what U and V give. Okay, well, I guess we just do that. I am just going to copy these. And I'll note that instead of bs.y, so let's do, I really hope this random guy's code that I copied works. Or formula. Bs is a position. So that's going to be P1 of 1. And then Bs of x is P1 of 0. Or technically Bs was supposed to be P2. Maybe I should just do these manually. I'll do these manually. As is P1 of 2. P1 of 2. And then, wow, these were terrible names they gave. Direction vectors, okay, so A is 0.1, B is 0.2. AD is the direction. So this is V2. You know, I'm just going to do this. I'm just going to use their names as much as I don't like it. But I do need to replace AS with this. Okay, and then what this is going to be is P1 is AS, and then this will be AD, and this is BS, and this is BD, and then we could do dot Y is going to be colon 1, and dot x is going to be colon 0. Okay, and now the new point intersection. So first, if u is less than 0 or v is less than 0, then these do not intersect. If they do intersect, then the intersection point is going to be bs of 0 plus bs of 0 or bd of 0 times v. That's going to be the x. And the y-intersection is going to be bs of 1 plus bd of 1 times v. And now the question is just if x and y position each at least and at most. If xi greater than and should be at least and the yi, oops, this should be 4. How many intersections? Let's hope that this code works. Oh no, it does not. Why does it not work? If we get division by 0, then here. Actually, let's just look at. Okay, so these velocities are the same. If they're the same, then they just intersect everywhere, or sorry, they intersect nowhere. So I think we just fail. If one of them is the same, no, they have to be. Okay, I just need to submit something at this point. I'm sure I'm falling behind. So I think if we get a divide by 0, we just don't count it. I think they just don't intersect unless they're exactly the same. And we hope that this is it. Rank 4, okay. Doesn't seem like any hailstones will naturally collide. Find a rock. If you throw it just right, you should be able to hit every hailstone in a single... What? Reach energy... Oh, I see. Oh my... I have no idea how to... Oh, if you throw the rocket times 0, where do you need to be so it perfectly collides with every hailstone? Wow, okay. So... This is... So basically we need to find the time. There's a few things we need here. I think this is maybe just a massive set of equations. So let me start like writing things out. So our position is going to be, let's see, OX, OY, OZ. I think we need the Z's now, right? Yeah. And any given rock's position is this, Vx, Vy, Vc. And we also have our throw Vx, throw Vy, and throw Vz. And this, so there must be an intersection between these two. That's our first constraint. And it must be, maybe I should represent these generally. So let's do like, O is our start location, and then T is our throw vector. And this is the position and the velocity. And basically, I don't like this for throw vector. I'll just pick M for no reason. Okay, and the O plus T is like time elapsed, must be equal to P plus T times V. So this is a requirement. What are the unknowns here? The unknowns are O. O is all unknown. T is unknown. And M is also unknown. Or sorry. Yeah, M is also unknown. It's really annoying because this is like a quadratic terms. It's not like they're becoming... The problem is this, because it's not like we're waiting for all these rocks to become collinear. It's that we are waiting until we throw such that by the time our throw arrives, it'll be on that line, which makes this tricky. It's just annoying because these are like quadratic terms. Maybe I could just throw this into Sage and like solve it in Sage. Sage solve system of quadratics. Can it do that? Underdetermined. It must not be underdetermined, notably. Does it need to be integer? Any integer position and any, oh, we only throw integer velocities. Okay. So for starters, we have D. So let's just like print D and we'll copy it over into Sage where we'll proceed to work with it. And oh, I forgot to set D equal, didn't I? Just trying to get that junk off my screen. Okay. And I think this is integers. Yeah. So what we're gonna do, QF solve quadratic forms. How does this work? How does this work? Matrix QF solve takes in, oh, this is specifically quadratic forms. That's not what I'm interested in. To find the equation system. Where are the quadratics? Is it just solve? How do you, what's solve quadratics, SageMath. Is there any way to reduce this from like some general quadratic? That's the other thing I need to think about. Because if there is, then this is going to be how do I, wow, I actually don't remember how to use variables at all, or how to use Sage at all. Oops. Wrong button. There it is. I mean, oh, this just works. Can I give it systems? Wait. Why is not defined? How to define variables for equation Sage? I can't believe I forget to do this. I think it's something like, oh, var. Okay. Does that just put it in scope? It does. Okay. Is that how solve works? Sage. Oh, what do you know? Look at that. Yeah, maybe this will just work. Oh, do I need to say over integers? Solve over integers. Has anyone solved it yet? Seems relevant. So one person has, okay. Integer lattice, ZZ. It's not integer though. I don't really want to use assumptions though. These are like constraints. There's some syntax like this that I've used before, but I really don't remember what it is. This is like obviously not going to be brute forceable by any means. This should be generally solvable, right? No. Field. Polynomial ring field. I don't know if this is what I want. Let me just see if this works. Ooh, no, okay. I have no idea how to use Sage right now. It's been so long. And I'm not even sure if even when I knew how to use Sage back then, I'd know how to do exactly what I want to do now. Integer variable. Is assume really the way to do it? I feel like what I want to do is solve over the integers, not make assumptions. Assume integer. Okay, well, anyways. So what are the unknown variables here? This is known. So there's only 4 unknowns here. So maybe I don't even need all the equations. Or maybe I do. Okay, well, anyways. So our variables here are going to be, and then the velocity we throw with, and then the point and the point velocity of the rocks are known. Those are fine. And then t. I thought that was how that worked. Oh, it's var. Oops. Okay. And what we'll do, set up a bunch of equations for px, py, pz, vx, vy, vz, and d. The equation we have is that, so there's 3 equations. There's ox plus t times mvx is equal to px plus t times vx. And then we want the same equation for we want the same equation for y and z. So I think those are just all our equations. Did I turn caps lock on? No. Okay. This is very slow. And I think those are just our equations. I mean, this just like seems right. And oh, I wonder, could we use these equations to like, oh, wait, no. Oh, crap. No, that's not right. Shoot. So the actual equations, maybe I'll write these in, oops. Maybe I'll write them in idle so I can actually edit quickly. Oh my God, this is not being quicker right now, that's for sure. Yeah, my bad. I forgot that they all intersect at different places. Oops. So specifically, there is a intersection. Let's do this. And then ti will be a var T plus string I. And then it's this. Yeah, okay. So these are like all different T's. And then we also need to keep track of all theirs. And initially this will just be these. But we're gonna add all our TIs to this because we need to solve considering all those. And I think that should work. Well, work, quotation marks. And now what we do is for v in all theirs, assume v integer. And then I think we'll just solve equations for, wow, it's really chugging on just assuming integers. Curious? No, it's not what I wanted. Where am I going to? Really? Why is it so slow? Solutions are coming in. I wonder if there's a better way than just chucking this into a solver. I haven't even thrown it into a solver yet, so this is like weird. What V did we get to even? T131. Okay. I'm very not optimistic that this will solve, but and then assume v integer. Oh, okay. Well, did not know I could do that in the Sage console. Is it getting slower? But why? I haven't even, I guess I wrote the equations, but surely it's not doing anything with those equations as I do this. But I guess I'll just let it go. And eventually what I'm going to call is solve equations. And I care about solving for all variables, right? So I think this is what I'll do. Why is this so slow? It's not even solving yet. It's just assuming integers. Ugh. Maybe I should have assumed integers first. I have no idea why this is slowing down. Oh. I guess I could do more research while I'm doing this. This is just the, this is specifically conics, right? Yeah, this is like a very specific, this is like quadratic forms, which I don't, can we write this as a quadratic form? I kind of doubt it. Wait, can you just write everything as a quadratic form? Am I being dumb right now? I don't know what vertex form is. Is that? Is it called a vertex form? No, vertex form is like this thing. Oh yeah, I should just write this as a quadratic form and use this dedicated function. But this is over Q. Oh wait, Q is rationals. I guess I could just tell it the field, maybe. Maybe I'll try that. So first of all, how do I convert a quadratic into this? What format is this? I like to play with it, but this is still running, and I don't really want to interrupt this. Ring entries. Okay, so what we can do, minus px minus ti times vx equals 0. This is the form we want them in. Let's just call this. I have no idea what solve returns, but I guess I'll just run this and see if it works. Meanwhile, I'll try and write the quadratic form code. So this is 0. Let's rearrange that these are all have 0 on the right. Okay, so these are our quadratic equations. And then the given lexicographically, that's so weird. Can you just show me what the thing is? What is n? Oh, it's a matrix. Okay. Okay. Well, I'll figure it out. And then we'll do. I'm gonna need to import default dict and Sage. Coefficients will be. We'll just do default dict. The coefficient is 0, and then what we'll do is. Oh wait. Oh, all terms of degree 2? I have some terms of degree 1. Can I solve that here? Is there an easy way to inject lower order terms? Wow, I have no clue what I'm doing. There's not some other solution to this, is there? Should I think more about that? I'm gonna have all these equations. What can I do with those equations? Anything? I have no way of figuring out progress of this. Should I just Google the general problem of like, point such that it intersects others at, the times are not integers either. I guess one thing that's true is that these velocities are very small compared to the actual coordinates. I can think of some like heuristic approaches, but somehow I don't think it's going to cut it here. What is like the general way of doing this? It's just like drop the Sage thing. Okay, that's no way. This is like manually solving. I want like... S boxes. It's like cryptography stuff. This is linear again. If your system is linear in what you care about, does this become easier? Like, it is linear in what we care about, right? Which is O. Why couldn't you give more details in this answer? So as to easily keep things reduced modulo the relations. Solve system of nonlinear equations for linear variables. Problem is these t variables are different in each equation, so you can't actually really do much with combining equations. Oh. Wait. What? Does this mean that we just have way more variables than equations? Or like we always have 6 more variables than equations? Because the t variables are different in each one? Oh. But this is definitely not going to work then. I want to kill that. Is this solution really unique? It probably is by the fact that these are integer. Man, I am very lost on how to solve this. I don't think setting up a big equation is going to work. Or setting up a big system of equations, I mean. Because this is ti. Let's also do this. So one thing that's, I don't know. I mean, I guess I can write this as we don't m is the same across everything. Oh wait, no, my bad. We have 3 equations. 3 equations because we have 3 coordinates. And each of these 3 equations adds only 1 new unknown. And adds... Is there like a way we can iteratively refine our guess? I don't really think so. Well, anyways, let's do this. Yes, we add 1 unknown for every 3 equations, and then we have these like 6 other unknowns. So it should be in principle possible to solve. If this quadratic forms thing would let me put in non-quadratic terms. That would be really nice. I guess Solve is probably trying to do it symbolically. No. This is definitely not. Yeah, that's like an AES thing. This is very not useful. I guess, oh, can you solve for the X, Y, and the Z separately? Oh, maybe you can. No, because TI is fixed. Wait, was my part one solution even like correct? I'm like confused now because of the. Oh, it was just when the paths cross. It wasn't colliding. That's right. So that was fine. And now we're perfectly colliding. I'm almost surprised that this isn't. Like, this seems like a natural question to ask in some sense. And I'm surprised that it's as hard as it is and that I have no idea how to do it. Of course, that's still going. I tried to terminate this and didn't even accept my keyboard interrupt. So the problem and the reason this is quadratic is that we have this times this. If we can either fix our velocity or fix the time we intersect with a given rock, then this becomes a linear system and it's easy. Given enough points. I don't think we could really brute force over velocities. Oh, wait. Like, I'm trying to think what the order of our velocity will be here. Because these are, like, really far away. Maybe I find, like, two of the furthest ones and sort of think about what I would have to... how those constrain me if I need to hit them in a certain order. Again, we don't need to collide at integer locations or integer times. Wait, but these are integers. Is that a coincidence? No way of knowing. It doesn't seem obvious to me either way. If it did have to be integer collision times, is there anything we could use that for? I guess we could obviously trace out a trajectory from each of these. And then we could try and figure out which ones are like collinear, but let me find the rock that is like the furthest away from everything and has all positive velocities. So, well, no, that's not gonna be the first thing we hit. Is there anything we could like binary search over? If we have a location, we can like play with the speeds. We can't do these separately because of the time that we collide with a given thing matters. If this problem were in 2 dimensions, how would I solve it? If we fix our position and our velocity, then it's like all the rocks just pass through the origin, and they're the correct position and velocity. Then all the rocks pass through the origin at some point in time. So maybe we could try and like guess a bunch of positions and velocities and see what gets things closest to the origin. I don't know. Seems weird. Maybe brute forcing velocities is the better way to do this. Our velocity needs to be integer, and assume for starters that it can't be that large. Then this problem is like a linear system. It won't be solvable most of the time. But like if there's 200 velocities we need to try on each coordinate, and that's being generous, it's a lot of things to try and solve. Realistically, it's going to be more like 1,000. And that's a little questionable. maybe we can solve like least squares and then sort of proxy the fact that like how close we can get to all zeros is a measure for how close our velocity is to correct. I could just try that. So let's try solve for solve given v. And so we have our set of so the variable here is mx. I'll just call it this. mvx, mvy, mvy, mvz. And then the equations are going to be unknown. So what are the unknowns here? Ox, oy, oz. That's not unknown. This is unknown. And then we're fixing this so that this is known. So I think these are our only unknowns. And what we'll do, so this means that our first equation, so first the x, so that's the coefficient on OX is 1, the coefficient on, this is our matrix, and this is our things needs to be equal to. So the coefficient on OX is 1, coefficient on OY is 0, OZ is 0. Coefficient on TI is going to be this thing, so that's going to be MBX minus BX. And the thing we need to be equal to is plus PXI. So plus PX. And I think we just do this for all of our coordinates. And oops, it's A now. NumPy NumPy.linealge dot, let's do least squares. And that should be a massive vector. Whoa, doesn't like something. Why is this vector not big? Do I need to transpose something? Where's it printing? It's so many lines. I want to stop that. Okay, thank you. Come on. I thought I typed an equal sign. Okay, there we go. Oh, probably that's what I need, maybe. Oh no, I think I needed. Yeah, there should be how many unknowns? 300 times. That's how many equations we should have. The number of unknowns should be. Oh, whoops! I forgot TI is an unknown and TI is different. Ugh. Okay. Yeah. So this should be zeros except for. Keep making this mistake. I still don't even know if this is gonna work, by the way. I'm just saying that. 0, 1, 2, 3 plus I is equal to mvx minus vx. That's what I wanted to do. Okay. And let's fix this up to use, that's z, that's y, 1 here, 1 here. So I go to the b dot append, px, py. Was that just the bug I had earlier? Maybe. Okay. Then oh, come on. Why am I keep doing this? Also, that was okay, so 303 unknowns. I think this checks out. And we should get Archond. Do I keep getting that warning? I only get it once. Okay. And I'm getting so I think these are my coefficients, which I actually don't care about. And then hope these numbers aren't too big that I'll lose precision. This is, I have no idea what this is. Is that like how close I was? Maybe. I don't know, let's just try it. Wow, I really hate this warning. I have no idea what this should be. But, and if we start going that direction, it got a little better. So I guess now, a thing we could do is we can figure out for in, let's start at minus 1,000 and then plus 1,000 and go by hundreds. Also, this should be the result is going to be solve given, can't type, solve given v, vx, vy, vz. And if I guess we just try it, see how much better we can get. It's going down so little. Oh man. I'm doing, how many? I'm doing 20 cubed right now, and it's this slow. It's pretty fun. What needs to actually update if we wanted to try something better? This is so bad, man. Did Sage ever spit anything out? It did not. It wants the velocity to be larger than 1,000, I think. Is there any way I could do like a gradient descent style thing on this? I mean, I probably could. Should I just try that? Maybe I will. So let's do given how slow these solutions are coming in. Oh, it's almost capped. I think I'm not gonna get it. It's pretty sad. But given how slow these solutions are coming in, I am suspecting that this is a very heuristic thing and that there is no solver you could just put this into that'll spit out the right answer. That or it's some crazy sophisticated algorithm, and that's why it's taking people very long to write it. But yeah, let me try and do this gradient descent thing. So per score. And then what we can do is we can see how much it improves if we go step size in each direction. And how do I want to do this? Okay. Okay, and then what this should be is an approximation of the gradient. So it's like if we change it by that much, how much does our score change? I think technically I want to do some dividing by something, but I'm not going to worry about that for now. And basically what we'll do is we should update proportionally to these. I think our step size right now needs to be like, our learning rate needs to be like 1e minus 28. Let's see. So if it goes down, we want to go in that direction. So it's actually minus equal. I think just this. I'll probably need to do some tuning here. What is it not like? Can I not write format strings these days? What the? Oh, it's because it's a matrix. Does this have a dot squeeze? Maybe I'll just cast it to a float. It's not getting much better. Oh, it's because curse score is not improving. Or curse score is not being updated. It certainly is going somewhere, though. I worry it's going to find the non-integer solution, and that solution being integer is like a very important part here. Let's bump up the learning rate. It's going kind of slowly. Now it's oscillating. Or is it? Oh, it's getting better. And what we'll do Really? It's settled there? Also, this can be a forced print. Was it getting better? It was still getting better at the end is the problem. Yeah, it being integer matters quite a bit, apparently. Sad. This is still going down. Probably there's like a bad initialization here. Probably this is not, yeah, obviously this is not like a convex thing, right? I mean, I could start it off with the best place we found. Well, the best place we found is not even as good as this, right? This is like 1E27. I can start it off somewhere else though and just see what it does. Learning matrix maybe start a little bigger. Well, is the gradient here just like basically 0? What? How is that? Our step size is massive, right? Oh, or maybe... we could do a hacky thing, which is set this to none, and then set it equal to 1 over and what this will do, will on average move a third in each direction. So we want to move more than that. Let's move like 10. Move like 100. Make it big. I mean, it's certainly going somewhere, but I don't think we're ever going to get to the actual answer this way, since it will just end up in some local optimum. Yeah, this is like not even that good of a solution. Another possibility is that least squares is just not the right thing to do here. Like if our velocity is off by a little, what does that do? So, yeah, this is a pretty crappy solution. Oh, whoops. Maybe this is part of the reason. I only wanted to normalize it the first time. Maybe it wasn't the reason, but... I don't think this, changing that would get me any better results. Should I try something completely different? I bet leaderboard's full by now. Okay, leaderboard is full, so I can take my time and do this without the pressure of leaderboarding. It's a little sided in leaderboard. I'm curious how far I fell for that. Oh, I didn't fall at all. Oh, I guess I didn't really see many of these names in the top solvers in part 2. It might be that because part 2 is like super mathy, it's Shawu is here though. It might be because it's super mathy. It's the usual speed coders like myself do not leaderboard. Well, anyways, yeah, how to do this? I wonder. Yeah, this is not going anywhere, that's for sure. The gradient descent thing. I mean, I think it is true. If we happen to guess the right velocity, they should just give the right answer. That's probably something I should verify, though, with the sample input. And make sure I don't have like some awful bug there. Okay, well, if it can't solve the sample input, it's not looking so hot. Oh, well, I am starting it over here, that's why. Well, that's probably not why, but that is a reason. What is the optimal velocity to use? -312. Interesting. Watch this to be non-zero. Okay, it is 0. Well, that's almost a little disappointing, because if it were non-zero, it would mean that I have something to fix. But this just means that the approach is flawed. It's probably true, though, that this looks pretty like non-convex. I don't know. I'm a little curious about... Well, it is certainly increasing in that direction. Is it? It must be non-convex, right? Right? Am I going the wrong direction? I'm definitely not going the wrong direction. But... Oh, my step size is pretty big here. Maybe that could be part of the reason. It's kind of getting somewhere, right? Okay, but this is for sure a local optimum that it is found right now. And based on these values, I think. So let's try this. Okay. And the claim is that if we go like a little bit in some direction, it gets worse. Let's verify that this is true even if we go a little bit in the direction of the true answer, which is -312. So that would mean -0.6. So the direction that we need to go in is this, plus 86. Plus 1.14, and then plus 1.12. So let's go a tiny bit in that direction. And watch the solution get worse. Oh no, it got better, right? That still got better. Step size is too big, maybe? Oh, hey, it's getting there. My step size is too big. Oh, no. But now it's... Oh, probably... Yeah, it can't get to within that precision because of the step size being too large. Wait, so if this thing is convex, that's a game changer. Holy... Okay. Oh my god. Was that it? Was that like the right approach? Well, it's certainly going quite slowly now. I worry about precision issues. Let's increase the learning rate for starters. Oh yeah, if it was improving slowly, but then the lowering learning rate or changing learning rate was not the right thing to change, probably. Heck, can I make this even bigger? Okay, now it's going. Oh man. It's still going kind of slowly though, considering that we're at 1E27 and we need to make it all the way to 0. But but it is going. I think learning rate should be way bigger. Whoa, that did not help, right? Too big? Oh, that's not too big. Okay, I lowered my learning rate, and then it had an improvement. That's cool. Oh, I realized I didn't reset not improve, but I think that's okay. Hopefully I didn't lower it too much. Yeah, now it doesn't look like it's improving. But it's at integer coordinates. Should I just start it here and see what it does? But these integer coordinates can't be correct, right? Aren't they just way too small? This is just like way too small. Oh, this is the velocity. Oops. But it's going to be non-integer, right? I need to solve it exactly. Whoa, what happened? Does not like what I just did. Oh, that's why. I mean, I could just try it here. Like, the fact that these are integer look very, let's say, interesting. And I guess 1E17 is maybe not that much to be off by when these coordinates are on this. Maybe it's just like a rounding error. But if it is a rounding error, then we're not gonna actually get our precise answer this way. But we think the velocity is this. Whoa! It was off, but it was sub. This is the real value it's getting. Okay, show me the velocities are these. Oh, but these don't look like precise enough to be integer. I need more precision than that. I don't care about the other things, but can I get the whole value? Yeah, that's not, like, I could just round to the integer, but I don't think it's gonna be right. We'll try it. Nope. Okay. I think what I might need, if I have the velocity exactly correct, like, I am fairly confident that this is the correct velocity, given that, like, how do I get like a precise solve here? I guess I can do Wait. I'm starting the right location, but it's like spiraling out. Whatever. I don't actually need this. I'm quite confident this is correct. So let's get our matrices. This is an integer matrix. And this should also be integer. If I just tell it to solve, oh, I have too many equations. This is overdetermined. So I only need the first few of these. Singular. Is it? Oh. I also don't need all of these, right? Because now I have 303 equations, but then I effectively have fewer than that many unknowns because we're not using all of them. Okay, so if I use k equations, I'll have how many unknowns? I have 3 unknowns plus every 3 equations introduces another unknown. So that many unknowns. So the number of equations I would like to use is going to be 2/3 k is equal to 3, 9. K is what? K is 2/9. 9/2. Want 4.5 equations? Well, I guess what I can do is I can do this. This seems fine, right? If I do this, then I don't get, yeah, okay, I just need 5 equations. But these are not integers, are they? Oh, they're integers. They're integers. It was least squares being the problem. Oh, that's beautiful. You love to see that. This has to be it. Yes! Okay. I didn't make leaderboard, and I wasn't even close to making leaderboard, but I am happy that that worked. Okay, so wow, that is a tricky day. I'll give a brief explanation. I don't want to go on too long because it's already been over an hour. But I think part 1 was like kind of not that hard. You're given these positions and velocities, and you're told to ignore the third coordinate. So they're just like 2D positions and velocities. And this describes like a particle moving. And it basically just says compute all the intersections of all the particles if they intersect. And if they, oh, it says in the past. Anyways, and if these paths, and check just compute the number of paths number of intersections that happen inside of some region. And that region is like x at least 2, what is this, quintillion or something? And y at most 4 something million. And there's only 300 of these things, so you just do it. You just like loop through all of them. I think it was this, yeah. And one thing to note is that it is possible. So I think one gotcha here is that the formula for intersection of 2 rays, which is what these are, is really just a formula for intersection of 2 lines, where your lines are described by like a point and then a direction, which is exactly what this is, position and velocity. And you could get an intersection that makes sense for 2 lines, but doesn't make sense for 2 rays. So for example, if you have a ray that's like here going that way, you have a ray going here that's going this way, and suppose that the test area is here, it seems easy to me to write a bug where you conclude that the intersection is right here and it's inside the test area and you're good to go. Because if you ask for the intersection of these 2 lines, you will in fact receive this point, but this point is like not valid for these 2 rays because they're not, right? They don't go backwards. And that's what it means when it says they crossed in the past here. Well, anyways, I just copied this formula from some random Stack Overflow post online because I couldn't be bothered to derive it, and I obviously do not have this thing memorized. Turns out that was a good decision because it did get me 4th place. But yeah, so I did that. And then I just like, oh yeah, the way to check if they're in the past. So specifically what this formula gives me, I was actually pretty lucky. The formula I found gave it in this format, but it gives you a u and a v. And basically what that means is consider this like the velocity vector, and this is the position vector. So v and then x. What it tells me, or let's call this x1 and v1, and let's call this x2 and v2. And I'm still using the example where they don't actually intersect, but just imagine I'm using the example where they do. What this thing tells you is it like the way you solve this is x1 plus u times v1 must be equal to some point, and it must also be the case that x2 plus u times v2 is equal to this point. And this is just a system of equations, and you can like solve exactly, and that's where those formulas come from. Oh, sorry, this should be v. And just to say it explicitly, since these are the same point, they're equal, which is like you're finding the places where these are equal. And u and v, you can, if v is like in units of meters per second, for instance, u basically is the number of seconds that it takes to reach that location. And if u or v is negative, that means that one of these had to like go backwards. And that's how I like do this check very easily. And yeah, and then beyond that, it's just like actually compute the intersection location by like evaluating this. I only do it for one of them because you only need it for one of them, and then just check if it's like in the range, and if so, increment, and then you're good. So that was part 1, and part 2 was substantially harder, to say the least. Part 2 says, okay, well, first things first, you now need to worry about the z-coordinate, which is like obvious, expected. And then it says, now what we care about is you can throw a rock from any location and with any velocity you like, and this rock will hit every single, like you can throw it in such a way that it will hit every single one, it will exactly collide with every single one of these particles at some point in time. And it's asking you to find the position you need to throw the rock from. It wants you to like sum the coordinates. So find the position and then add up the x, y, and z coordinates of that position. And yeah, this is like this is tricky. I think that I was thinking for a long time. Like you can set up a bunch of equations. They're like a little annoying to try and solve because of the fact that you will. So now we care about exact collisions. And you will collide with, also there's a constraint that you're at an integer position and integer velocity. I suspect that this is like way overdetermined. So this input is like specially crafted such that this is possible. In general, like for random coordinates, you couldn't do this. And like it wouldn't be integer, and even in general for like random coordinates, I think there wouldn't be an answer. I think there needs to be only like a few of these. Like this thing I did at the end where I only needed a few of these to determine it. Well, actually, but yeah, I think there's the number of unknowns you have is I could do this formula again to figure out, but if you have 300 of these things, I think it's too overdetermined. And you actually, there would be a unique answer, not necessarily integer, if there were fewer of them. Or there would always be a unique answer in general. And if you had too few, then there could be like more than one possible answer. Still not necessarily integer though. Well, anyways, so you can set up these equations, and what these equations look like in vector. Here, let me actually get my draw pad out now because I'm going to be doing a bit of drawing. In vector notation, what these would look like is you have like you have vectors. Let's use this. P. Let's use sticker pen. Pi. And this is the position of hailstone I, and you have some velocity vi. And we also have our start location where we're throwing the rock from. And we also have our velocity, which maybe I will call W. I keep picking new names for this. So this is the velocity we throw the rock with. And now it's the case that if you throw your rock t seconds later, know that this is not a vector, t seconds later, this is the position it ends up in. And this needs to be equal to the position of the hailstone at that time. And the problem here is that what are the unknowns here? So this is unknown, the position we throw from. This is unknown, the velocity we throw with. This is known, and then t is unknown. And the problem here is that we have a product of two unknowns. So this is like a quadratic equation. And solving systems of quadratic equations is significantly harder than solving systems of linear equations. So hard that I couldn't figure out how to do it with my fancy math solving software, which I like to use for a lot of different stuff, including some advent code problems. So that's pretty sad. Yeah, I spent a while trying to think if there's anything I could do about this. What I ended up thinking about and realizing was that our position is very large and our velocities in general are kind of small. There's no guarantee that the velocity of our answer will be small. Small as in like the values themselves are close to zero. But my first idea was, if you can just guess the velocity, and then you can fix this, then this becomes a linear equation. I don't know what I was trying to do here, but if you can fix this to some specific value, then this becomes a linear equation, and you can just solve it. You can solve it exactly. What is sad is that there's too many possible velocities to check, probably, to like do this brute forcey. I was thinking, so in hindsight, I think the velocities, well, I guess they didn't all end up being negative, right? Because these are all positive values, it strikes me that probably at least one of your velocities has to be negative. I guess you could start at like 0, 0 and go outwards. Never mind. Ignore that last thing I said. It's probably not true. But if you try like velocities from negative 200 to plus 200, that's 400 possible velocities for each thing. That's 64 million systems of linear equations you need to solve. And I guess that's actually probably doable if you are smart and realize that you don't need to solve the entire thing. So I kept constructing the entire system of like 900 equations, because we get 3 equations for each of these points. This looks like one equation, but really it's 3 because there's an x coordinate, a y coordinate, and a z coordinate. And I was using all 900 equations every single time. And solving a 900 equation system 64 million times is probably not doable, but maybe solving a five equation linear system is doable. And I think 5 is all you need, actually, which is what this thing at the end determined for me. Well, in any case, I think that might have been a feasible solution to do. That was the first thing I thought of, but then I concluded I couldn't really do that. So then my next idea was, so another disadvantage is that if we don't solve it exactly, like if the true velocity was, what actually was it? If this is the true velocity and we were testing velocity plus 200 minus 180 plus 110, which is pretty close to the real velocity, a normal linear system of equations solver will just spit out like no solution. And that is unfortunate. So what I thought about was, what if we can try and approximately solve the system of linear equations with least squares and look at how well we did. With the idea being that if we did really well for this velocity, and then we did like really poorly for this velocity, then probably this velocity is closer to the true thing. That was the intuition that I had for using least squares. And when I say closeness, what that means is like you relax this to an approximate equals. Let me actually write it. Let me do this. It means you relax this to an approximately equals, and the actual mechanics of that are that you solve the system that looks like this, and you just try and minimize these epsilon squareds. That's like basically how least squares works. I didn't need the error bars. I guess I kind of did, but you can write it like this too. Sum of epsilon squareds. And basically the thing that I was printing out from least squares here was this sum of epsilon squares. And I was just trying a bunch of different things and seeing what would get me close to the value. And the very first thing I did was I think I searched on like a grid so another thing I concluded was that 200 to 200 was too small. I would have to at least do 1,000 to 1,000 to be confident. Turns out my actual answer was like slightly higher than 200 in one of the coordinates. So like minus 210 to plus 210 would have been completely fine, but I didn't know that at the time. So I searched from minus 1,000 to plus 1,000, and I jumped by plus 100 in each dimension, or in each coordinate. And I was just looking for the one that was the smallest. That did not work the greatest, I suppose. Trying to see if I can find it. Yeah, I think. Kind of curious why it spat this out, but surely. Oh, I guess it never got to. Yeah, it was so slow. It never got to anything past minus 1,000, and I just ended up killing it, I think. But in any case, I think that probably, if it had worked correctly, it should have spat out something like plus 200 minus 200 plus 110 or plus 100 as the closest thing. But in any case, that wasn't really working out well for me, partially because it's too slow. So then I decided, what if I could use a gradient descent type thing? So I can hold on to I can look at this value. I can try changing the velocity in like a little bit in each direction, resolve the system, then look at how this is improved. And if it's improved in a good direction, then keep going in that direction, and otherwise go in the opposite direction. And that's basically how gradient descent works. Gradient descent often uses different like auto differentiation to figure out how much to adjust this thing by and in which direction. What I use is poor man's gradient descent, where you do numerical approximation. So you just you literally fudge each coordinate by a little bit by step size, and you just sort of check how much it changed. And that's how you can approximate the derivative in that direction, or approximate the gradient more precisely. In any case, I did that, and then I let it go, and I had to tinker with a lot of these values, but eventually it spat out what looked like whole numbers, which is really exciting. And the least squares was giving me like a very small value for epsilon, or for the sum of errors when I used that. So that made me pretty confident that this was the true velocity. Then I had to get the actual answer. And the problem is that least squares had a lot of issues with like rounding. And I was still solving the entire 900 equation system. So these rounding errors definitely like piled up. And when I just asked least squares for the actual things that it found for this, also let me make this clear. This is not an unknown anymore. But when I asked least squares for the value of S, remember we need S to, like, this is basically the answer. When I asked it for the value of S, it gave me something that were not integers. And when I rounded them to the nearest integer, and that was like not the correct answer. So I needed the exact answer. And what I ended up doing was I just ended up solving not least squares, like forcing this back to equality and solving it that way. And also not using all 900 equations, because you don't actually need all 900, you only need the first 5. I think you might have only needed the first 5 in general. Yeah, that might have that might have made my life a lot easier, wouldn't it? Well, in any case, I'm not gonna spend too much more time on this. That's Advent of Code day 24. Part 2 was really cool. I'm very excited to see all the other solutions that people come up with that are not this like gradient descent thing. This felt very hacky, but I do remember there was a question last year where I don't know if it was intended or not, but I thought about doing it, didn't do it, and then I found out later that someone who leaderboarded did do it, and it just like worked very well for them. So I guess if I tried this even earlier, I might have been able to make leaderboard this year, or this day/part. But yeah, honestly, I'm not too upset about that. I got 4th place in the first part, so that is dampening the blow from having no points on part 2. This is so funny though to look at. 7 minutes and then 1 hour, 19 minutes. But that's just how Advent of Code goes. Cool. Yeah, that is all I have for day 24. And I will see you tomorrow on the last day of Advent of Code.